A warm welcome to everyone once again. The mediocre teacher tells, the good teacher explains, the superior teacher demonstrates, the great teacher inspires, said William Arthur Ward. I'm indeed honored to introduce the great teacher of our session, Dr. Anurag Srivastava, who is working as a faculty of electric power engineering at Washington State University and also serving as the director of Smart Grid Demonstration and Research Investigation Lab, formerly called SGDRIL, within the Energy System Innovation Center, ESIC. Dr. Srivastava also has a joint appointment as a senior scientist with the Pacific Northwest National Lab, PNNL. He received his PhD degree in electrical engineering from the Illinois Institute of Technology in 2005, master's from IIT BHU in 1999. In past years, he worked in different capacity of different universities and labs across the globe. His research interest includes data-driven algorithm for power system operation and control, including resiliency analysis. Dr. Srivastava is serving as or served as an editor of IEEE transactions on smart grid, IEEE transactions on power system, IEEE transactions on industry application, and Elsevier sustainable computing and guest. A past editor for a number of other IEEE transactions and IET journal. He has delivered over 30 plus keynote tutorials, IEEE distinguished lectures in more than 15 countries. He is author of more than 3,000 technical papers, including a book on power system security, and has 4 patents to his credit. Power and Energy Group NIT Calicut expresses a sincere gratitude to Dr. Anurag Srivastava for accepting our invitation to be a part of this online ATAL FTP on application of artificial intelligence in power system operation and control, and spending his valuable time and efforts in educating the faculties, research scholars, and students from various colleges about. Over to you, Professor.
Thank you, sir. A warm welcome to our department, our session as well.
Thank you. So let me share my set of slides.
Okay, sir.
Are you able to see my screen?
Yes, sir.
All right. So thanks so much again. And today I'm going to talk about power system operation control and how AI can help. Let me know if you want me to turn on my video or it will be okay without that.
So it's your wish. You can turn on the video.
Okay. Well, maybe just for bandwidth, I'll turn out later, maybe when answering question. So the work that I'm going to talk about is with some example on how AI can be used in operation control, and what I hope that in the end, there are a lot of questions related to this so that we can make it as much as interactive as possible. So let me start with first, because we're talking about power system operation control, let me start with the control room. So in control room, which we monitor the power grid, and there are typically multiple screens, as you see here in this on this slide. So these desks are for different operators, and they are either monitoring reliability, someone is monitoring the ACE, area controller, someone is monitoring the wind and solar plants, renewables. And the ultimate objective is to keep the power grid operating in most economic way and also most reliable way, right? So when that happens, we have multiple tools to help them to do it. So those tools screens are shown here, which is typically for transmission grid is energy management system, and for distribution grid, it's a DMS. Now, if we operate our power grid with expected failure, like one line outage, one generator outage, or different things, these operators are trained to do that. And recently, at least in a couple of years, there has been different kind of extreme events. So for example, these cyber attack is one of that. And then we have seen a lot of hurricanes. India just had one in West Bengal and Orissa. So these kind of events are extreme, which power grid operators are not trained for. And also when these extreme events happen, we rely a lot on set of data. And these tools, which is typically driven by optimization, will have to have certain access to observability of the system with the sensor and communication link. If any of these becomes compromised or outage for some reason, then all this optimization might not converge. Now, we all know that as the system becomes more stressed, optimization convergence become an issue, becoming more and more nonlinear. So what can we do, in this case? Now, turns out there are more and more events which are extreme, wildfire or hurricanes, are increasing, storms, of course, are increasing more and more, right? And what it results into that if operator is in seeing the screen, they will see a lot of different alarms coming into the control room. And these alarms will make the life tough for the control room operator if it is a lot and lot, right? Because they need to find out that which one to focus, which one to fix. What does it mean? There are a lot and lots of data in the control room with alarms which need to be analyzed. And existing tools, which is mainly driven by optimization for the control action, may not converge being under stress. So given this scenario, what can we do, right? So power grid operators are basically, so this is the Washington map. Here, that's where I am. And we recently had wildfire, we had a lot of storms and wind. And all these conditions, we need to prepare the alarm to basically act on these. So all these events makes the power grid operator very puzzled and thinking about that what to do. So we do need more advanced tools which should produce the results in some way to the operators and tell them that what to do when these extreme events happens. These tools should help them to process those alarms. So if you remember, the number of alarms coming to the power grid will be more and more during extreme events, which are going to happen more and more, and we are already seeing it. Process those alarms and at the same time detect that where are those anomalies which are creating these alarms. Rank them. So rank the criticality of these alarms. Find out the root cause. Again, what was the original reason that these happened. Then classify it and then make an action, which is decision support. Of course, once we have these tools, we have to train them to use these tools. And we have to also train them that use your support team, either it's a crew member or it's your, at each control room, there is a field engineer, which is their supervisor. And also there is a set of support engineers who will analyze different set of data and different set of system condition to support them. So with all these, requirement, and to do all of these alarm processing, anomaly processing in a short time period, we need to look at the two different solutions. The one which we have now, which is based on state estimation, you wait for data to come to your server room, which is in control room. From those server database, you take out the set of data, solve the state estimation, which happens in 4 seconds, in 10 seconds, or whatever the frequency is. And after state estimation, you do the contingency screening, which happens in minutes. And then from there, if something is going wrong, then you try to take the control action, which is typically driven by AC optimal power flow. As you can figure out, during the stress condition, a lot of these tools like state estimation will not converge. And that means that all the other set of action will also not happen. So in this scenario, if we know how to analyze the data with limited set of data available and process this set of data either through machine learning or through data analytics and use that in support of already existing state estimation and other set of tools, security and alarm processing, it will be ideal. So now next question is that how do we do that? Okay, so advanced tools, of course, we know that we need to develop it because there's a need for that. And these needs are demonstrated by the historical event. So if you heard about 2003 blackout, which happened in US, in Northeast US, in Canada, and in New York, and Pennsylvania, Michigan, that is the biggest blackout that happened in US. And one of the reasons was that state estimation stopped converging in Michigan state, one of the first energy operator. So we need a backup tool when normal system operation and these tools will not be working. Once we develop these tools, we need to validate, we need to integrate, and also think about human operator. So to make it happen, we are talking about a bunch of data, which is coming from all the server rooms, right? So you get a lot of digital set of data. You get some data from the substation. You get some data from the, if there's any circuit breaker with the digital relay, you get some data from there. You get data from the PMUs. You get data from the relays, and also EMS. Sometimes it processes it, sometimes it does not, right? You also have these cybersecurity software, which is installed sometime. So in essence, from SCADA, from PMU, from system status and EMS, we have enough set number of data that we can analyze through machine learning and data analytics. We'll call it advanced tools, where we want to flag anomaly. We want to find out the root cause. We want to not only use machine learning to find the anomaly, but also use like reinforcement learning to make a decision at that time when your physics is not supporting because of mathematics being under stress. So again, just to emphasize, our existing grid monitoring, which is based on ACOPF or any power flow, we all know that if you stress the power flow to make it more and more nonlinear, then it will not converge. And the reason is obvious, because power flow is a Taylor approximation of a nonlinear set of equation, which is we get from matching the power injection with the line flow, right? That's what the power flow equations are. And if it become OPF, optimal power flow, which is our existing set of decision-making tool, mainly other than planning tool and creating some rule base that we use, which might still work. We are hoping that using machine learning and data analytics, we will solve those set of problem where mathematics and physics will not support. Finally, we do want physics to support, because any solution that we are producing need to solve the power grid operation, right? But not necessarily mathematics. And once we create the set of monitoring and set of actions from these tools, we need to make sure that these are trustworthy. Why? Because state estimation is driven by physics, which means that whatever we do from the existing state estimation and EMS, we know that the control action will hold in the field. With machine learning and data analytics, the problem is there's no physics in that. And if it's not the case, then it is only doing what data is telling you. not what is behind the data. So we need to find the trustworthiness. We need to put some metric or maybe solve a quick power flow after this to make sure that what is coming out of machine, we can trust it. And on top of that, we need to make sure that human operator experience is being utilized. And working with a lot of psychologists and cognitive science, I figured out that human operator also has their zone where they perform better. If they're very much stressed, they will not be performing very well. If they're very much relaxed, they will not be performing very well either. So we need to use this tool and give them action to take during this narrow band of their full attention. Because finally in the power grid control center, they are the one who are going to take action. We are not looking for driverless car here because it's too dangerous for the power grid operation. We can also measure the human performance and their decision making. There are some human performance indices from cognitive flexibility to which is ability to take the action under stress, and eye tracking, and operation span and backward digit span, which is this part. Now, this is something which is very interesting to me, but today the focus is these set of tools, right? Data-driven and AI-based situational awareness, anomaly flag, and decision support. So let's talk about those tools. So what do we want in the power grid is if any set of data is indicating that there is anomaly in the system and we are going or drifting away from the expected normal operation, we need to detect it. When we detect it, there are two possibilities. Either it's a sensor problem or data problem. So that's one possibility. Now, a data problem can happen because of sensor, because of failed cyber network, or because of server problem. All those will point to me, it's a bad data. My grid is doing okay. It's just that data is wrong. The other anomaly that can happen, which is not really an anomaly, it's an event in the system, which is a fault or generator outage. So any contingency that is happening in the system is also an anomaly because it will cause my system to drift away from the normal operation. And we need to detect it so that I can take action on that. Once we detect the anomaly, we need to classify it, what kind of anomaly it is. We already talked about that. It could be bad data or it could be an event. After classifying it, we need to find what kind of event it is. So that's a further classification of event. And that's further classification of bad data. And that will help me through root cause analytics. So root cause will tell me that this event happened because a lightning strike on the transmission line. Or this generator went out because someone, cyber attacker, manipulated the breaker status through relay by logging into the digital relay. So I need to know that. We need to use a lot of data from the cyber side and from the physical side. But once we have that, we can do the root cause analytics. And then we will have a lot of alarm. We need to rank them, how critical it is. And after that, we need to take some action. And so these can all happen behind the scene, which means that operator do not need to see that how I'm doing it, how I'm applying my machine learning, because they want to see minimum information. They want to see what is useful for them. And this is what they want to see. They want to see that what is the status of the power grid. And if they need to take an action, it is a remedial action, which means corrective action, or it is a proactive action. They need to do it because something is going to happen for sure. So all of these is only possible if we process the set of data, either machine learning or data analytics, which is part of that, or AI, which will be also part of the machine learning. So let's look at what data we have. So we have two different kind of data. One is fixed data set, which does not change often in the system. And one is measurement or dynamic set of data, which is changing in time. So fixed data set is like how many generation plant we have. What are the parameters for that? How many substation we have? What are the parameters for that? Because substation, anything that will change will take years and years to build a new substation and add into database. Then we have transmission line, transformers, distribution line, customers. All are static and changing very slowly when we build it. But these are a lot of data. These are really a big data set. And then we have a streaming set of data from SCADA and from PMUs. So if we take this PMU set of data and we try to find out that how much data it is. So let's assume that there are 100 values per second being reported by PMUs, and there are 30 reporting rate per second. If you have all 100 points in a substation or PMUs, then average data rate will be around 10,000 per second. For a total of 100 substation, for a balancing authority, it will be 1 million per second. And for reliability coordinator, which is a very, very large area, will be 10 million per second. If I tell it to data scientist or machine learning scientist that 10 million per second, how much data it is, they will say it's not big. It's not a big data problem. It's still less. But it is a real-time data analytics problem because we need to process that as soon as possible. And that offers challenge. But once we combine that with a static set of data, it is a real big data problem. So what does big data problem do? And what does data analytics mean? So you have a set of system, which is a physical network here, your generation, transmission, big wind farm, distribution system, industry, home, electric vehicle. And then we put a lot of sensors to monitor that. And then there is this big cyber network, which we can, of course, put any different technology, including software-defined networking, with a bunch of IoT devices, which we don't have much now, but we will have in future. And then we can have wireless, we can have a fiber optics, we can have microwave, all these things. And then there are multiple platform or server to analyze those set of data. And then we want to make a business application out of this. So all these set of data we want to analyze and find out that what is the status of the grid. And if any anomaly happened, why did it happen? So what does data analytics do, or machine learning? Before you apply machine learning, we have to analyze the set of data. And different thing we can do is, predict the future, explore the relation, find out relevant application, actionable insight using that, and of course, database processing and query based on that. And especially it becomes very tricky when we have a cyber attack, because then we don't know that which data to trust, which one to not do. So based on those data scientist typical task, we can categorize this data science analytics before even applying machine learning. Is how do I move between my different database? So the database of generators set of data, the transmission line data, and I need to move between them smoothly as soon as possible to analyze and find the root causes. I need to find the interfacing management. Then I need to find the relation between the different data set and group them. So that will call clustering. To find the relation, I can use regression. I can also find, so this is time domain correlation. This is spatial correlation. And I can do that with the graph theory or network science. And then after doing all of these, I can apply machine learning, either deep learning or reinforcement. So in deep learning, we know that what is the target that we want to get there. In reinforcement, we don't know. We don't tell that what is the target. We only tell my neural network or what were the technique I'm using that you did well or you did bad. So reward function. And then I need to visualize that set of data so that human operator can process it. And data science comes again there too. So in the power grid, we have never adopted much data science and machine learning. The reason is two things. One, our power grid is very dynamic, which means that we don't have a static set of data which has been already used in Xbox face recognition or Facebook face recognition. That's the static data set processing. That's not a dynamic. Reason number two, in power grid, we need to know that not only that what is data is telling me, but why it is telling me. What is the physics behind that? When I do this maps prediction, it is only spatio-temporal correlation, which is easy to do in Google Map. And finding out and telling and by voice that take me home. And Google Home based or Google Map based will do that. And to also predict that how much time it will take to go from my home to office or office to home. Amazon Alexa, which is a good application of NLP, natural language processing, which process my set of data and reach out to the cloud, analyze those set of data and return the feedback back to me. All of these are possible because of connectivity and because of advancement, of course, in machine learning, which is trying to find the good set of database. Some of these are going to help us in the power grid also, right? Amazon Siri or self-driving car, even though it has been experimented from a long time, it has not made into the field much. And the reason is, again, ability to operate in dynamic environment and trust that we put on the machine to make it happen. So some of these technology we can apply, but we have to be careful that we understand that what can go wrong with machine learning and analytics. If you all know Stephen Hawking, he said that AI is likely to be either the best or worst thing to happen to humanity. What we make out of this and what will happen, future will tell us. But one thing is very clear, that these machines will only do what we tell them to do, at least right now. And we have to be very careful that we use it in knowing that what can go wrong. Two things that can go wrong is we use bad set of data or incomplete set of data to train it. Second, we use not a good quality machine learning. Now, typically, when we apply machine learning to the power grid, we are going towards the library. We're not going to develop our own. Even if we develop our own, in 2 to 3 years or 4 years, we cannot develop very good machine learning, or robust machine learning, or explainable machine learning. So we are going towards the library of machine learning algorithms, which are developed by multiple different set of researchers, scientists. And like we know that Google has a very good library, TensorFlow has a very good library. And a lot of these Google OpenAI are the good quality AI, but may not be very good for all the application. So for example, we all know that even a slight change in face, face recognition. Even if you do a slight change, like these days with COVID, I'm having a mask. With the mask, my phone does not recognize me. And typically my phone is set up to open as soon as it detects my face without entering any password or without entering any any code. So slight change in my face might result detecting the face, and MIT has taken a very good quality machine learning from Google and proved that it might detect a human face as a pig face. Okay, so these are the papers published on this, and that shows the danger of only data driven. So I always believe that in the power grid, when we apply these things, we always have to do validation before we take that control action, and that validation has to be driven by physics. So let's talk about some use cases. So we have a bunch of data coming from physical system, from cyber system. Cyber system will have a network data, network traffic data, packet data, host, which means the device data, in log file, IDS, intrusion detection system alerts. And from physical system, we all have SCADA data, PMU, breaker status, relay operation, and all these things. What I want to do, I want to do the anomaly detection classification, localization, and then process all this set of information to finally get to the correlation and prioritization. The final goal that we want to get to is situational awareness and decision support. There are two parts: knowing that what state I am operating, situational awareness to the operator, we are normal, alarm, emergency, or a blackout. And then the most important thing is this decision support, which is if the system is not doing in the way we want to, what control action to take. We call system operation in normal mode to maintain the reliability. If we are trying to maintain the system operation into extreme event, adverse event, then we'll call it resilience, right? So reliability is under normal operation. Resilience is against extreme event. Reliability does not hold into extreme event because the system is not capable to keep providing power to all the connected loads. So we'll define what is resilience, and all of these set of action will help me in monitoring and enabling the resilience. The short-term planning and proactive control is also part of that, which will help, and we'll talk about that. So let's start with the first one, anomaly detection and classification. And what we want to do here is we get a set of data, stream of events, and several different sensor data, and ontology, which means that where it's coming from, we know that, and relation. And we want to detect anomaly, detect event, classify events. So to do that, we develop a set of tools which we call Chronos, and there has to be some database, which typically already is at the control center. We want to visualize it, we want to question it, find correlation, which we use Granger causality. So first thing, if I want to do this detection of anomaly and detection of event, I have to find some set of algorithms from the data analytics and machine learning, which will help me to detect anomaly or departure from the normal operation. So very simple one, like linear regression, even neural network edge regression. But this is very simple. Linear regression will tell me, and we do want not very complex set of algorithms. We want to keep it computationally low, which works, which is more robust. And even applying a simple linear regression will tell me some outliers and will tell me some missing data. And set of normal set of data, it will find a regression are fitting into that. Chebyshev method has a 2-layer of upper and lower threshold, which we adjust based on the sampling of data. dbScan is a clustering method. This can also help me by forming a cluster, so density-based clusters, which means that it automatically takes the new set of data, put in a one cluster, and cluster is based on our definition. We need to tell that how far to look. So if you find a data set, this becomes its radius. If the new data comes, it belongs to that bubble, then it becomes one cluster. If it does not, then it finds its own place in of course, current voltage or whatever it is on y-axis and time on this axis. And finally, after a certain time period, I will have some of the data point which is not part of any cluster, and then other data point as part of this cluster. Typically, if I have a data point which is not similar to any other data point, it's anomaly, or at least the possibility anomaly. So the single data point becomes a. But what we found, again, our system being very dynamic, it does not work all the time. So we applied long short-term memory. That also does not give me results all the time. And finally, what we learned that if I put a real set of data, that some are detected by linear regression, some are detected by dbScan, some are Chebyshev, some are LSTM, and there's no single winner, which means that one method does not work. And that is expected from a dynamic system like a power grid. All machine learning data analytics require a tuning effort, which is a big challenge. How did we set the parameters for neural network? Also, we do not have enough training data. So what does it mean? Probably an ensemble-based technique, which combines the results from multiple simple techniques, will help. If one does not work, it's okay. Other two will work. And we will go with the majority. And also with ensemble-based technique, we need less and less parameter tuning because it's not a single technique, so we don't need to adjust. We'll normalize it anyway. And then it improves the performance, especially if it's unsupervised, because we don't have a lot of set of data to train it. And once we do this data anomaly detection, then we can further use the physics, because to classify the event, we know that any set of data which is going through inertia of the system will slowly change. Any anomaly that happens, if it is caused by the power grid physics, it will follow the inertia. Any bad data does not need to follow physics. So using that relation, I can divide that. I am not going through all the details, but these are in the papers. I can use the spatiotemporal graph of the power grid and divide into the smaller system to find out these set of clusters, and then finally classify that, those event, and localize it. So this is a good physics-driven machine learning. Another thing that happens in the power grid, which is very unique, is a concept drift, which means that what is normal now is not normal after 1 hour. At 8 a.m. peak time period and evening time peak, we know that system is loaded heavily, while in the night it is not. So what is normal in the night is not normal in the peak load period. And we need to detect that there is a drift in the concept of anomaly. And we need to process that using some kind of data drift detection module. Again, the detail is in the paper, and we need to process that, pre-process the data, then do the anomaly detection, and then finally classify and localize it. We can further expand this set of anomaly detection with additional set of cyber data, especially if I'm trying to find out the root cause, which happens to be cyber manipulation, cyber failure. And in this case, we'll use the SCADA to use as a trigger based on the breaker status and topology. We'll use the streaming PMU data with Auto-encoder, which is a 2-layer of neural network put in a 2 encoding and decoding algorithm. This is semi-supervised method. You train it for normal, not for the abnormal or anomaly. Then cyber set of algorithm, which is not a time series data, so it's very difficult to apply a machine learning into cyber set of data. But you can apply rule base, and you can learn the rule using fuzzy logic or using other spatiotemporal convolutional neural network for the cyber data. Keeping in mind that those are not time series data where the neural network works best. And then based on all the things that we learn from SCADA, from PMUs, from streaming cyber data, we can further check again with log file, validate, and then finally declare that it's a cyber event, this physical event, cyber physical. And then from here, we can further branch out the root cause, location, and why it happened, right? So all of these things we can do it, branch out. We can prioritize which we should fix first. And finally, of course, the ultimate goal is the decision support. So next part becomes, after doing all of these, awareness, decision support, is resilience monitoring. And resilience, I think I already defined it, that in extreme event, it is all about critical loads, because we cannot focus on all the loads, so it's not a reliability. And ability of the system to supply its critical load will be the resilience. There are multiple task force in IEEE, in SIGRE, that I'm involved with, and we are trying to define the resilience and how to measure it. FERC, which is a federal organization in the USA, which monitors and maintains the reliability of the power grid, defines resiliency as ability to withstand and reduce the magnitude or duration of disruptive event, which will ultimately relate to anticipate, absorb, adopt, and rapidly recover. So we made multiple tools. This is CP-TRAM tool, Cyber Physical Transmission Resiliency Assessment and Monitoring. And what we do, we take a lot of factors from the power grid, which will influence my ability to not supply critical load, which, as you can imagine, it depends on the network topology, it depends on the control at the resources, it depends on the location of critical loads. And all these factors which are listed here is going to impact that, physical factors. Same thing for the cyber factors. We can get a number of factors which will impact my ability to supply critical load. We will combine these factors using AHP, which is analytical record process, which is multi-criteria decision-making process, very frequently used in business and finance. If you have multiple factors you need to integrate, you need a multi-criteria decision-making process. AHP is one of those. Then we need metric, and then finally cyber physical resiliency metric. So these are some example of resiliency calculation using multiple factors, which were listed in the just right here. So we calculate that, we have developed the equations for that, and then finally we get resiliency metrics for the physical and resiliency metrics for the cyber by combining these factors. And then I can rank a different defense mechanism in the cyber system, which will enhance my resiliency. So here, these are the security mechanisms which we can apply in the power grid cyber system. More authentication, more monitoring, more access control, encryption, and then I will see that how my resiliency is changing. The next part is validating those tools. And to validate those, we need a test bed. So we need to model the cyber system, we need to model the physical system, and then we need to keep those tools that we just developed, AI-based tools, anomaly flag and anomaly detection tools, and we need to feed the data to these tools. So these data has to be generated in real time. Of course, if I have access to real system, I can directly use that, but I'll not be able to validate, because any anomaly that's happening in the system, I don't even know this anomaly or not. So I need to generate that. I can generate that in real time using simulators. This one is OpenRT. I can use RTDS. I can interface with the real relays, real sensors, and then collect a bunch of data from here, and then finally validate my set of tools, because here I will create the anomaly. I will create the cyber attack from here, and then this will impact my power grid operation. I can create fault. So anything that I want, I can create the anomalies and see that if I'm able to detect it right way or not. So this is how my control room look like in my lab here at WSU. This is again the control room like setup, and this is where I generate set of data. We also need to have a cyber model, which looks like very close to real field. So we have simulated that, not simulated, but we have modeled it using a real set of hardware and switches and routers. Historian, we have an EMSA in server, which was GE from GE EMS. We also have from Inksys simulator, and multiple server to host my intrusion detection for the cyber grid. And then I can model scenario like a GridEx, which is done by NERC, which is cyber attack on the power grid. We do it at national level in US. And then I can see the impact on this. So this is another scenario, which is a Ukraine attack that happened twice, 15 and 16. And power went out in the, so we re-simulated in our lab. And this one shows that email was sent for phishing, and one employee clicks on that, which is still an IT side, and the malware was installed, and from using that malware, attacker was able to reach to the substation. So this is modeling a substation, and these are the actual devices. And then finally, once attacker has all the access, it sends a command to open the breaker, multiple breaker at the same time to open the transmission lines. And that resulted into multiple circuit breaker outage or opening, and then finally the transmission line outages and resiliency going down. So this one shows that resiliency is going down as different steps are happening by the attacker. If we had these tools to monitor the system, we will take action. And if you take action, my resiliency will increase. So in all these cases, my resiliency will increase. So again, this is just an example. So finally, some results that I will very quickly go through, which you already have seen. We have applied into IEEE systems and WEC system, which is Western Electricity Monitoring Council, which means all the west of Mississippi River. Of course, the system is 23,000 bus system, but this is a reduced high voltage system, which you can also download. It's a publicly available. And also some example for that. To do the anomaly detection and event detection, we will use this metric that how well I can detect all the bad data that I introduced in the system. And precision is, so recall is ability to find all the bad data. And precision is only find those, not find any false set of good data as a bad data. And then our result shows that we are very successfully identified using that ensemble-based method with LSTM, long short-term memory machine learning, and with DB-scan. Very good result in 99%. I was also able to detect my different set of event and cap bank and everything that we modeled. I was able to detect. Sometimes I'm not able to detect because the signature is very small. The payload increase was very small and I don't need to detect it. And then also for the concept drift, we model different scenario where the concept drift resulted into not being able to detect anomaly using the simple ensemble-based approach, but by using this auto-encoder with concept drift trigger, we will be able to detect events which was missed in the past. And this is for resiliency metric by simulating multiple case studies, line outages, 2 transmission line outages, 3 transmission line outages, which is my more interest because this is not a normal, it is anomaly and extreme events. We are able to detect and show that resiliency will go down. As you see here, resiliency is going down. And then finally, for the cyber system, we model multiple security mechanisms, and we also see that security mechanism impacts the resiliency score. That's what is expected. And then finally, we can combine these two together, that resiliency monitoring with ability to detect anomalies and without ability to detect anomaly and fixing it. So if you fix the anomaly, your resiliency score will show the true number. Otherwise, anomaly will, if it is a bad data, then also resiliency will go down, which is not correct. And that's why putting the anomaly detection and classification before resiliency monitoring is required. Just like Amazon Alexa, I can also put this NLP in the power grid, in the control room, and I can allow my operator to query different things in the system, and based on that, ask software tool to tell them that what information they need. For example, they can ask that I see this anomaly. Can you find a correlation between these two anomalies? My tool will do it and return that. It can ask what is the lowest voltage in northern part of the grid. My tool will query, find out, and give the results back. This is very useful when the power grid operation is under stress, which means that operator is also under stress. So by asking question, we can make it easy for operator to find information. We implemented in lab using natural language processing and SQL query. and using the REST server. Finally, we have a lot of problems in the power grid and a lot of technique in machine learning. We need to find a very good match. And before applying machine learning, we need to question, do you really need it? What's wrong with the existing grid operation algorithms? And it's reliability, economics, stability, security, cybersecurity, DR integration, or cyber attacks. So when we do that, it's very important, then we should apply machine learning data analytics for the right problem. In our case, justification is that state estimation and other tools will not work under stress or under nonlinear operation. So machine learning and data analytics was used for anomaly detection, classification, event classification, and localization, prioritizing the alarms, and resilience monitoring and decision making. Again, we have to very carefully analyze the power system problem before deciding that which machine learning suits it, and before that, do we really need machine learning? Maybe the existing way of doing things is very fine. And typically, we can apply machine learning if it is a data-rich problem and system model is not available. For example, forecasting. We cannot develop a function which will take the input, give you forecasting. We can try doing that through regression, develop a function, but we can do better with the machine learning. If model is available with rich data set, and if we cannot solve using physics-based method in good timeline, then again we need a machine learning to do that. In this case, event detection can also be done by looking at scatter data and relating it to the physics. And that will take time. With machine learning, I can do it faster. Typically, in highly complex and dynamic problem, machine learning is not a good candidate, at least now. If we make a major breakthrough machine learning for a dynamic system in future, then maybe it will be good to apply for transient stability. Right now, I personally think that transient stability is not a good method to apply. Contingency analysis, not a good method to apply. I can do it with physics. With the parallel computing, I can get very fast results. Validation is very important. Double validation before we apply machine learning based decision making, because there's no physics behind it. So we need a major breakthrough in explainable AI and using right technique for the power grid operation. With that, I would like to thank again all the organizers in providing this opportunity. Here is my email address, and I'll be very happy to answer some questions.
Participants, kindly put your questions in the chat box, or you can send it to the panelist.
So I see some question posted in the Q&A.
Sir, there is a question there. How to formulate the data set for a prediction problem like power quality disturbance prediction, fault prediction, and power swing detection? What should be the input taken from the power system? This is a question from one of our audience.
So I don't see that in chat. Is that in Q&A or it's in chat?
So it is in chat, sir.
Okay. Yeah, so let me...
Sorry. Send to you 1 second, sir.
Sure. So how to formulate data set for prediction problem like power quality? So all the data set that we decide There is not a single answer to that. Now, if we are looking at the power quality disturbance prediction, then it means that we have to look at the historical power quality events and find out what decides that, and then use your best guess, the input for that, and find out the correlation. Is that spatial or temporal? And then based on that, we need to decide which input will be good. After we find out the inputs, then we need to do the feature selection, which means that this is data-driven feature selection, which is going to give you additional input data. And that's a correlation between this derivative of that if you give it time. So there are automatic tools which use 3 set of data and generate 10 set of input data now, because you have processed those few features into expanded features, which feature selection tells that it might be good to consider. Now, of course, this is based on the sensitivity-based analysis, which is internal of that feature selection process. So the sensitivity-based correlation is very important to narrow down the set of input which should be considered in any problem. Same thing here too, which is power quality disturbance prediction.
Hello, hi, Anurag, Prof. Anurag. I'm
Yes.
Biju from Kerala. So nice
Hey.
to see you virtually. Hi. Nice to see you virtually after this degree. Very happy to see you here.
Thank you. Good to hear your voice.
Yeah. So thank you for your nice presentation on AI techniques for grid integration. I have some general questions only. Nowadays, especially in here in Kerala context, a lot of rooftop solar PV integrations are coming up, and especially in the context of lot of plug-in EVs are also coming up. And the government of India and government of Kerala is giving a big boost to this renewable energy integration in the grid. So how can we apply this AI techniques, especially this machine learning, for the generation forecasting for this RES integration?
Yeah, so just like we do a load forecasting, now we have to do a DR forecasting, and there are some work already going on into this direction. The problem is it has to be aggregated, because at least in US, we don't have measurement or data coming from at the household level. The only data that we get is smart meter, which does not tell me that how much is the EV and how much is the solar and how much is the actual load. What we get is the net load consumption from the smart meter. So as long as we use that smart meter load data and do the prediction for behind the meter, to do that, so for solar, so we have to divide the problem into solar prediction, because that's a little bit easier compared to electric vehicle. Why? Because in solar, whatever is being produced is dependent on the weather or solar insolation. And if I can put one sensor in, let's say, 2 by 2 miles, typically I can extend my sensor data for validation in that region. So using that, I will call it behind the meter solar prediction. And by doing that, I can isolate the net load into the solar prediction and the actual load. Then next comes the electric vehicle, which is much more difficult problem, because first, it is charging and discharging both. Second, there is no other sensor data that I can put. For that, we need to do a lot of estimation. And we need to get into city database. Typically, when you buy electric vehicle, then you put a charger in your home. And based on that charger, you need a city permit, at least in US. And based on that city permit, I know that who has electric vehicle and who does not. And then for that, we need to make some certain assumption based on their signature of power consumption. Because every time it's being charged or discharged, I will see a big dip or big increase in the power consumption. And both of that signature will tell me that it is electric vehicle and we need to aggregate and then start doing prediction. So those are the possible things. We have applied random forest. We have applied LSTM. So we applied a couple of techniques which we call behind the meter prediction. And that's one possible way to do it with minimal sensor data and using other set of data, which is of course weather and signature based load change.
Okay. For this kind of predictions, is machine learning is a right technique, or we should go to regression based method, which gives better result?
So both are good. Regression typically works in more predictable or more less uncertainty of data. While neural network, because it can model, or especially the deep neural network, it can model the correlation into multiple dimensions. So that's what the main difference between regression and so as much uncertainty is in the data that we're trying to predict, machine learning should be better. But if you're trying to do load forecasting, which is not very complex regression is better, or regression will work. It's not that regression will give a better performance than machine learning if you have a right machine learning selected. But machine learning will be, of course, heavy computation-wise compared to a regression. So load forecasting, it's good. For load forecasting, I think, especially behind the meter thing, machine learning is better.
Okay, thank you, Anurag. Thank you.
Sir, there is another question. Whether the reactive power control of the inverter can be achieved through machine learning without disturbing the other voltage regulating components?
Yes. So I did a project with Siemens where we used reinforcement learning to take a reactive power output from the inverters while still keeping up with their limits. And in that case, we kept two different control layers. One was slow control using the transformer tap changer and capacitor bank switching, which is more slower. And inverter-based control, we kept it at fast rate. So Siemens has that set of algorithm, which hopefully they will implement sometime. And definitely reinforcement learning works, but it does not need to be reinforcement learning or machine learning. You can, and this only makes sense when you have very, very large system. And we want something to work at a substation level. For a system where there is not many inverters, we can easily do a two-layer of optimization. One optimization will be at slow scale, centralized, and the other one will be decentralized at the high, very, very fast time scale with all the inverter slave. In Pullman, we also have a battery. We worked on such a control, which is sensitivity based, which is much more simple. And again, this is two-layer battery doing its own control with inverters, and the transformer tap changer and cap bank doing its own. So there are three different possibilities to do that. That I was involved with. I'm sure that there are more possibilities to do that, but machine learning definitely can be applied, and reinforcement learning makes more sense to me.
Okay, sir. So, any queries from the participant side? Ma'am?
Yes, Deepak. Professor Srivastava, this is Sunita. Hope you remember me. Last
Yeah.
year, yeah.
Yes, yes.
Together we submitted a proposal for Spark.
Yes.
Last
Yeah,
year.
yeah.
I think the results are not yet published due to this pandemic situation. It is in the pipeline. Okay. So anyway, I thank you very much for spending your valuable time for our FTP. It was a very nice session. Thank you. Thank you very much.
Thank you.
Sir, one more question, sir.
Yes.
Is there any difference in the output of monitoring algorithms for data missed due to PMU failure or communication failure and data missed due to cyber attack? Are the monitoring or classification algorithms able to recognize them or classify them separately?
Yeah, so we typically do it in 2 stages. In fact, 3 stages. The first, we identify all the anomaly. It doesn't matter that it's an event or it's a bad data because of PMU failure or communication failure or cyber attack. And once we identify the anomaly, which is the first stage, then the second stage, we will classify it. And in classification, we need more set of data. That will include cyber data. And we had these set of rules that if it's a cyber attack, then you will see a signature in the cyber system data. And that will be correlated with the physical system anomaly observed. If it's a PMU data, bad data problem, then cyber layer will not show any communication failure, but only PMU data, which will be correlated in a temporal domain, not in the spatial domain, because it's a single set of data. Remember that power grid, any event that happens, it's like throwing a stone in the water in a river or lake. So it will spread in a spatio-temporal domain. So any event that happens, that's how we detect that it should be represented in spatio-temporal domain. Any event which is any bad data which is caused by one single PMU data will be only temporal, not in spatial, because it will not spread in the system. It's not a physics-based event. Any communication link failure will be represented again in temporal domain and in the cyber domain. So all of these has a unique signature, and as long as we know it, we'll detect it and classify it.
Okay, sir. Thank you, sir. One more query. Sir, is it okay?
Sure, yeah.
Thanks. In OPF problem with renewable integration, which MI technique will be preferable? In OPF problem, which renewable integration, sorry. In OPF problem with renewable integration, which ML technique is preferable?
So it really depends that what kind of OPF you're solving. Now, if it's not under extreme events, then I think the mathematical based optimization is best because it keeps the physics and I don't need to revalidate. If we are solving OPF problem in extreme events where my mathematics will not work because being a very nonlinear under stress system, then I believe that reinforcement learning is one possibility. For example, we just have the question about inverter-based reactive power control, which is OPF problem. We solved it using reinforcement learning. And the advantage of reinforcement learning is that once it's trained, it is able to work in a lot of different scenarios at much faster rate. And because there's no target needed, so it's a semi-supervised, which is good because in OPF, we do not have a specific target to reach to. So all the neural network or other kind of optimization technique will not work. And then there is a third technique, which is hybrid technique, where we still use the mathematical approaches, but their parameters, their initialization, we support using machine learning technique. That requires classification technique. So random forest, clustering technique, all will help in selecting a parameter, selecting a sensitivity of those parameters, initialize the parameters for my mathematical optimization, and make it converge much more faster.
Okay, so will be the last question. One more, sir. Sorry to. As you said, we use ML techniques only for relevant applications. Is it good to use for power quality disturbance prediction and fault prediction?
So I think power quality disturbance prediction, it will make sense, because any prediction, typically we cannot develop a function. We cannot develop a mathematical function which will predict that when the power quality disturbance is going to happen. It typically depends on multiple different set of data, which is the system itself, which means network, loading condition, and event, which might happen at that given time. And because there are multiple parameters which we cannot use and develop a function to predict these power quality disturbance, it should be a good possible application of ML. For fault prediction, I think even machine learning, because fault prediction is very, very difficult. The first thing is that fault itself that happens in the power grid is quite random. So if you're trying to do fault prediction in a component level, which is triggered by some number of inputs, like a circuit breaker failure, because we are monitoring its electrical parameters and mechanical parameter, and there is a mechanical assembly which follows a certain trend. So we have to have certain trend that we are trying to use as a features to be used by machine learning. So in fault prediction, if you can identify those, I'm not aware of what will be those, because it's quite random. Fault is, like a lightning strike, animals, or someone driving and hitting the pole. So these are very random event which results into the fault. But those kind of fault at the component level, which is driven by certain number of parameters, in that case, again, fault prediction can be done. So it depends on the definition of fault prediction itself.
Thank you, sir. Thank you for sharing your experience and.
Thank you.
Hello, sir. Thank you. Thank you so much, sir.
Sure, thank you.
Hello, sir.
Yes, hi.
Gratitude can transform common days into Thanksgiving, turn routine jobs into joy, and change ordinary opportunities into blessings. On behalf of Power and Energy Group, NIT Calicut, I would like to express my sincere gratitude to Professor Anurag Srivastava for having a great session with us. Thank you so much, sir, for spending your valuable time and effort for this section despite of your busy schedule and odd times. I hope this session gives a clear picture about artificial intelligence-driven solution for power grid operation and control. And also, it's going to help us in forming our curriculum and research work. Once again, thank you, sir, for your time and guidance in shaping the young mind. Thank you, sir.
Thank you, sir. I will mail you later, sir, regarding this workshop.
Sure.
Okay, sir. Thank you. Thank you so much. Thank you, sir.